Welcome back. So, in the last class we were discussing about how to fabricate an interdigitated electrodes, right. So, what I have shown you is if I want to fabricate an interdigitated electrode on oxidized silicon substrate, what are the processes, correct, and before that we have seen the substrate which is silicon and how silicon is manufactured from the bowl. So, the next step would be to create a SU 8 well. So, let us see what we want to do and then we will continue. So, if you see the screen, the class was on understanding the fabrication of integrated circuit, and we talked about silicon, we talked about the clean room, we talked about the process, then we came to this particular slide, and then we have seen how you can create or fabricate interdigitated electrodes and interdigitated electrodes, right, with metal, that is chrome and gold. I said that chrome is used to improve the adhesion, adhesion, adhesion of gold, right. So, we have seen that, Now, we have not seen that how you will deposit this gold, what is the technology to deposit the gold, that we will discuss in the next lecture. This lecture, particularly this particular module, is to understand how we can finally fabricate a sensor with an SU 8 well. You see, this is a well, right. You see this entire section is a well, and there are electrodes inside the well. So, how we can create this particular sensor which is shown in E in this particular figure, right, E, you see. And what is the advantage of sensor? That once you have this sensor, if you place the tissue on this interdigitated electrodes, then you can measure the impedance, of the tissue, right. Initially, when tissue is not there, your impedance would be, like I said, infinite. When you place the tissue, you will see the change in the impedance which you can measure. It is not anymore infinite, right. So, the idea is that let us have this kind of sensor. This sensor can also, we can also call biosensor, or we can say MEMS, micro electromechanical systems based sensor, all right. So, we are looking at this particular process so that we can finally understand the MOSFET, all right. So, this, if you see this particular image, this one, all right, what we see is there are interdigitated electrodes with a spacing. So, the width width is 10 micrometers and spacing is 10 micrometers. While if you consider this image, the width is 10 micrometers, but the spacing is 30 micrometers. All right, and you can see a greenish color. Can you see greenish color here or greenish color here, right? This green color is because of the oxide layer on silicon. This green color is because of the silicon dioxide. We will see how we can grow silicon dioxide as well in the following lectures, right. Now, you see this particular color which is brownish, right, and that brown color comes of SU8. Actually SU8 is transparent, but when you deposit SU8 on the oxidized silicon substrate, you will see the change in color. This is an optical image taken from the metrological microscope, and within this SU8, that is why you can see here it is like a well, right, and the interdigital electrodes are within this well. These are the walls of the well. This is a wall of SU8 well, and in this well we will place the tissue, alright, that is the idea. Okay. So, now let us quickly see what we have understood, how we can design the interdigitated electrodes, and then finally how we can design the SU8 well, that is the idea. So, let me draw here what we saw, what we have seen until now is you take an oxidized silicon wafer, I will draw 2 wafers, right. Then you grow silicon dioxide, this is silicon dioxide, what you are doing, you are growing silicon dioxide. Okay. And understand this thing, because the same kind of process steps you will use to fabricate your MOSFET as well, alright, silicon dioxide. Now, on this silicon dioxide we have to deposit what, chrome gold. We have to deposit thin layer of chrome followed by the gold of our required thickness, that is chrome gold, right. On this chrome gold we have spin coated photoresist, this photoresist was positive photoresist, correct. On this we placed a mask, mask was, the cross section of the mask is here, cross section of the mask, right. This is your mask, correct. And then this is which kind of mask? This is my bright field mask. Right. Let me write B clearly, bright field mask, correct. This much was easy. Then so what we missed, after we spin coat photoresist, we have to pre-bake it at 90 degrees centigrade for 1 minute, right. That means let us start from scratch. Silicon oxidized silicon, that is silicon dioxide we have grown, on that we have deposited chrome gold, and we have spin coated photoresist. After photoresist we will pre bake for 90 degree, then we will load the mask and we will do the hard contact. Hard contact means two contacts are in touching each other, alright. Mask is touching the wafer spin coated with photoresist. This was easy, very easy. Now we expose this, wafer with the mask loaded on it with UV light, ultraviolet light, alright. What we do? We expose this wafer with mask loaded on it with a ultraviolet light. Once we expose it, what will happen? I told that if I use positive photoresist, then whatever the pattern is there on the mask, right. If my mask says S, then my wafer with photoresist, right, when exposed with UV and developed, I will get the same, I will get the same S. I can retain the pattern, right. So, if I use positive photoresist and if I mask is this, I will get a wafer which is similar to it, right. This is what we have understood. Okay. This is what we understood. Now, let us see once you expose it, what you have to do? You have to unload the mask, right, and developed photoresist. Once you develop the photoresist, how your wafer will look like? Your wafer will look like, your wafer will look like the one that I am drawing here. Like this. So, that means I have chrome gold, I have my photoresist. This is after developing. After developing, I will get this. After developing PR, I will get this particular wafer from this one. So, 1, I will write 2. Okay, I will write 2. Easy. Now, after we develop the photoresist, it looks like this. Now, what is the next step? Next step is we have to post bake it. Post bake 120 degree 1 minute, right. Post bake 120 degree 1 minute. So, that this gets hardened. This photoresist is a polymer. After exposing and developing, this will get soft. So, we have to harden it, harden the polymers, right. So, I am again telling you in terms of very basic experiments, alright. This itself is a whole course. So, do not get too much confused, you just follow the step: pre-bake, develop, post bake, pre-bake, develop, post bake. After post bake, what we have to do? So, this it will help the metal below it, not to get etched. The photoresist, if I see you here, right, and if you see the metal here, metal layer is here like this, correct, and the photoresist is here. If I put this in metal etchant, metal etchant, ETCH ANT, metal etchant, then what you will observe is the metal from all the sides will get etched except where photoresist was there, that means this photoresist will save my metal, right, will save my metal. So, it protects the metal below it, it protects the material below it, that is the role of photoresist. Okay. Now, once I have this photoresist, my next step is that I have to etch the metal. So, next step would be I will load this, or I will put this wafer in the gold etchant, right, followed by DI rinse, followed by chrome etchant, followed by DI rinse, right. This is the next step. After I have photoresist on this chrome gold, I will follow this step, which is I will first etch gold, then I will rinse it, then I will etch chrome, then I will again rinse it. Once I do that, what I will get, you already know what I will get. We will get the metal below the photoresist would be saved, it will not get etched. Metal that is our chrome gold will not get etched, it will not get removed, all right, and the metal from other areas will get removed, from other areas will get etched. Easy, very easy. Okay. So, if that is the case, what is my next step? My next step would be I will dip this wafer. Which wafer? Now, the wafer that I see right now in front of me, which is my wafer number 2, this one. I will dip this wafer, dip the wafer in acetone. Why? Because acetone will work as a stripping, it work as a stripper. Stripper for what? It will strip the photoresist. That means I will have only chrome gold. I left with chrome gold, and this is what? These are my interdigital electrodes. So easy, right? So, from silicon to chrome gold, we can do the following, or we can follow this process to get what is it? Interdigitated electrodes. It is like digits which are interrelated, right, but not connected to each other. You can see there is not connection, no connection. That means if I measure the that means if I measure the impedance between two electrodes, right, if I measure the impedance across this, then I will see infinite impedance, or resistance across this, infinite resistance, because metal is not connected, and in between metal there is a insulator, which is my silicon dioxide. This much is easy, extremely easy. So, from here what we got? We have got this particular wafer, this much. Which one? The electrodes, this electrodes, all right, this electrodes, this we have patterned it, excellent. Now, we have to pattern the SU8, right, because the electrodes were within the SU8. So, what is the next step? So, I will start with I will remove this, right. Let me remove it, and we will start with the wafer which is already having this interdigitated electrodes, this one, right, this wafer, we want this one. So, let us use this wafer and let us form the SU8 well, SU8 well. So interesting. So, let us remove this, let us remove this, let us clear the screen, let us clear the screen, and let us see how we can form the SU8 well, all right, SU8 well. Excellent. Now, what we have to do? We have to form the SU8 well. So, I will take the wafer, which wafer? Which already has the interdigitated electrodes. So, I can directly draw oxidized silicon wafer, on which I have chrome gold, right, chrome gold, right, chrome gold as interdigitated electrodes. On this I will spin coat SU8, all right. SU8 is a negative photoresist. Until now what we have seen? Positive photoresist, right. Positive photoresist, what happens? If I have a mask, then my wafer would have same pattern. In negative, this is my bright field mask. In negative photoresist, reverse happens. If I have my mask, right, bright field, my wafer everywhere I can have the, what you call, the material, except in this area, except in this S. So, S would be not there, other than S everything would be there, you understand. Opposite of this will happen, opposite of this, only this S would not be there. So, let me just quickly draw like this. This is, I assume that this is a metal, okay, everything metal is there, and if I use a negative photoresist, what will happen? Let us see. If I use a negative photoresist and I use a bright field mask, then exactly opposite of my bright field mask of positive photoresist, the pattern will be exactly opposite. Let us see. Okay. Now, my pattern would be very difficult. So, anyway, the point that I am making is everything would be, let me draw like this is better, except this area. So, you see here everywhere the metal is etched, right, metal is etched, here the metal is there or the PR is there, right. In this case only in this S region PR would not be there, other all the region PR would be there, everywhere PR would be there except this S region, everywhere PR would be there, alright. So, to give you a better example, you have to remember that positive photoresist same pattern. So, let me draw a wafer, same pattern you get. Negative photoresist, opposite of this will happen, opposite of this, where there is S there will be nothing, where there is nothing everywhere there will be photoresist, you got it, everywhere there will be photoresist. That is the role of negative photoresist. Now, what we have to understand, well, I will teach you negative photoresist in detail in some lectures. Right now, let us see that SU8 is a negative photoresist. So, when you have SU8 as a negative photoresist, you how can you make the well, right? Your idea is, your final idea is that you should have a substrate, right. Let me remove this. You have a substrate with interdigitated electrodes, and then you have SU8 well. This is what we want, this is what we want, right. This is the well, this is the well, this is for the contact, right. This is also for the contact pad, contact. Right. So, this is our final device, it should look like this. Where were we? We took the oxidized silicon wafer with interdigitated electrodes, and on interdigitated electrodes we have spin coated SU8, we have spin coated SU8. What is the next step? Next step is we have to pre-bake it, pre-bake. Now, how you know that what is the temperature for pre-bake, how you know what is temperature for post-bake, how you know that what is the next step when we use SU8, it is already given in the data sheet. When you get the SU8, the manufacturer already gives you data sheet which says that when you use SU8, you first pre-bake SU8 after spin coating at 65 degrees centigrade. After pre-baking, you use the mask. The mask will look like you will use a mask, and your mask will look like something like this. This is correct, right, or to be more precise, let me draw exact. So, we have to cover this area, alright, we have to cover this area. So, it will look like this, like this, like this, like this, and like this. Okay, this is good, alright. So, our mask is bright field mask, with a pattern as you see on the screen, This is the pattern of my bright field mask, My photo SU8 is negative photoresist, We will see positive photoresist, negative photoresist, mask, everything. Okay, this is just a quick example of a sensor, so that when I talk about other devices, you don't get confused. Okay, all right. So, I have my negative photoresist, which is my SU8, right. I have this bright field bright field mask. Now what I said, whatever this there is mask, whatever the pattern is there on the mask, opposite of that will happen when we use negative photoresist. Opposite of this pattern will come on the wafer when we use negative photoresist. That means that after this, after I do pre-baking, I will load the mask with this particular pattern. If you see, the pattern is covering the electrodes, you see here it is covering the electrodes, but other than electrodes is not covering any other area, is not covering any other area. So in fact, how about this? This is even better, right? This is even better. How come? I will tell you. Okay, how come I tell you? If you have mask like this, now what will happen? Now what will happen? What is the role of SU8? SU8 is a negative photoresist. Negative photoresist, the role of negative photoresist is that whatever the pattern on the wafer, opposite of that would come, or whatever the pattern on the mask, whatever the pattern on the mask, the opposite of that would come on the wafer. The opposite of that would come on the wafer. What does that mean? Let us see. Now let me repeat, the property of the negative photoresist is that if you use a bright field mask, whatever is there on the mask, right, the pattern on the mask, the reverse will come on the wafer, the reverse will come on the wafer. So that means that let me expose this wafer, let me expose this wafer with UV light, with UV light, right. Then what will happen after exposure? After exposure, in case of SU8, the manufacturer tells us you do post bake before you develop it. Post bake is done as 90 degree or 95 degree, right. If you understand in the positive photoresist, we were pre baking at 90 degree and post baking at 120 degree, correct, in case of positive photoresist. In case of SU8, in case of SU8, we had to pre bake at 65 degree. Before post bake, here after pre baking exposure we were developing, right, pre bake. So in the positive photoresist, let us write once again, it becomes easier when we write again and again for you as well as for me. See, pre bake positive, okay, we are talking about positive, then you have to expose, then you have to develop, then you have to post bake, right, pre bake, expose, develop, post bake. This is the case of positive photoresist, right. In case of negative photoresist or in case of SU8, what are the steps? What are the steps? First step is you spin coat, then you pre bake, then expose, then you post bake, followed by developer, alright. So you see here pre bake, expose, develop, post bake, here pre bake, expose, post bake and develop, right. So what we have done now, we have exposed it, we have pre baked it, we have pre baked this SU8 which is this one, right. So let me draw XX. So at XX pattern is your SU8, okay, this is SU8. So now what will happen? Now we have pre baked SU8, we have exposed the SU8. After exposure, what we have to do? We have to do post bake, and after post bake we have to develop it. Now what is SU8? SU8 is negative photoresist. Negative photoresist, opposite of this will come. Opposite of this will come means opposite of this pattern will come on the wafer. That means if what will happen? If I develop the, so if I am removing this, okay, You know what is this one, or let me write it down, let me draw it here, so that you understand what is opposite meaning, what is opposite of that meanings. The opposite of mask, the pattern on the mask means now I have a wafer here, wafer here, correct. I have electrodes, right, and now I have opposite of this, that means that my SU8 would be here, my SU8 would be here, my SU8 would not be here, my SU8 would be here, my SU8 would be here. You see if I draw XX, so that we understand where is SU8, where is SU8. What happens where the pattern was dark, right, there is nothing here, where the pattern is dark here, right, this particular area, right. So, let me just remove this, so you understand clearly again. You see this area and this area 1, 2 and 3, this 3 area on the mask were dark, right, and we got opposite of that, wherever the dark area was there, SU8 is not there, SU8 is not there, wherever it was exposed, SU8 is there, right. But in case of positive, we will get opposite of this, right. So, positive photoresist, bright field mask, same pattern on mask. Negative photoresist, bright field mask, opposite pattern on the mask, right. That means, you see wherever the dark area region was there, SU8 is gone, right. After this step, right, after this step means first we are done, we have pre-baked, then we have loaded the mask, we have exposed, we have post bake, then we have developed. When we develop, from 1 we get 2, right. So, once we have this one, what is this? This is your well within the electrodes, interdigitated electrodes within the SU8 well, right. These are interdigitated electrodes within the SU8 well. So easy, extremely easy. You guys understood? I think you understood. So, we will just see this all things once again in detail in some other class. Right now, let us understand that what we have done. We have done two things. One is we have patterned the interdigitated electrodes. On this interdigital electrodes, we have spin coat the SU8, which you can see on the screen. On this SU8, we have done pre-baking. After pre-baking, we have exposed it by contacting, by using a mask, right. We are loading the mask and then we are exposing using UV light. After exposure, we are unloading the mask. We are doing a post bake because it is SU8. This is what manufacturers tells us. So, we are following the process given in the data sheet. After post bake, we will go for developer, and in developer it is a SU8 developer, alright. So, this developer will develop SU8, whatever area what was exposed, whatever area on the mask that was exposed, SU8 will stay, and whatever area was not exposed, SU8 will go away, or reverse of whatever the pattern is there will be there on the wafer. And thus you can see here that we have this SU8 well, which is right over here. We have the area for taking the contact, right. So, now we have contact pads on both the sides, we have interdigital electrodes in the center of the well. So, this is what is this? This is our complete device. You see here, so easy, right. Now, what we have done here, we have used oxidized silicon. What exactly SiO2 is? SiO2 is nothing but SiO2 is SiO2 SiO2. What is SiO2? SiO2 is glass, right. So, I can use, instead of oxidized silicon wafer, I can use glass, right. So, let us see, what I have done here. I have used the glass. So, I have taken the glass substrate, correct. Then I have deposited chrome gold, easy. Then after chrome gold I have spin coated photoresist, right. Then I have pre-bake it, this is positive photoresist, positive. Then I have pre-bake it at 90 degree. Then I have when I attach the mask, mask has some pattern which is similar to what you get here, right. After attaching the mask or loading the mask, I have exposed this wafer with UV light, then I have developed it, and then I have post baked it. After post baking, after developing and post baking, what I will get? I will get a photoresist just on this area, right. Then I will etch this wafer, that is etch chrome gold. When I do etching of chrome gold, what I will have? I will have this particular substrate. So, when I am showing you this particular substrate, glass, chrome gold, then directly this, that means this all the steps are done here in section B, right. After chrome gold we are spin coating sorry after chrome gold we are spin coating photoresist, positive photoresist. On after spin coating photoresist we are pre baking at 90 degree. After pre baking at 90 degree we are loading the mask. After loading the mask we are exposing the wafer with UV light. After exposure of wafer we are developing the wafer. After developing the wafer we are post baking the wafer. After post baking we are removing the gold and we are removing the chrome. When you remove chrome and gold, after that we are stripping off the photoresist with acetone, and you get section C, right. This whole process we do to get section C. Now, on this section C, that is a glass with interdigitated electrodes, right, patterned electrodes, we spin coat SU8. You can see here we have spin coated SU8. On this spin coated SU8, what we will do? We will pre-bake it, then we will load the mask, we will expose the SU8, right, and then we will do post baking, then we will develop, and then when we develop we get this particular wafer, this particular glass with interdigital electrode in the SU8 well. You got it. So, whatever I am talking, whatever I had told you today, right, or in this lecture and the previous one, the process is very easy. We will once again see the process of photolithography, and then you will understand in a better way how you can fabricate, or what are the process to fabricate a biosensor or a interdigitated electrodes inside the SU8 well, interdigitated electrodes inside the SU8 well, right. Now, once you have this sensor ready, you can use for several application. If you read the papers, what you will find that people have used to measure the impedance of the cells, human cells or mice cells, right, and to see what is the change in impedance. If I load different drug, what is the change in impedance? These are cells, red things are cells. People have also used, right, tissue, directly place the tissue instead of cell on this particular interdigital electrodes, like you see here, right, and measure the impedance. So, this is a sensor that you have. This is the sensor that you now know how to fabricate, or at least how to understand the process flow to fabricate interdigitated electrodes inside the SU8 well. Now, what we have seen? We have used masks, right. We have used mask. What kind of mask we have used? We have used bright field mask and we have used dark field mask, right. we have seen in morning a bright field mask, right. So, right now what you see on the screen, it can be bright field mask. If you assume that the white is transparent and this is your pattern, what I have written is this is your bright field mask, right. Dark field would be opposite to this, dark field would be opposite to this. Now, and I have shown it to you in morning how the bright field mask looks like, or in the previous lecture how the bright field mask looks like, and we have also seen how the dark field mask looks like, correct. So, once you have the mask, what are the defects in the mask? So, once you make this interdigitated electrodes and you have SU8, then you can have interdigitated electrodes within this SU8 well. This is how a silicon wafer will look like, oxidized silicon wafer with interdigitated electrodes, and these interdigitated electrodes are within the SU8 well, alright. So, this is how you can your wafer will look like. This is a 4-inch wafer, 4-inch oxidized silicon wafer, right. If I want to draw cross section, the cross section is oxidized, so oxide, no, let me draw properly. If I wanted to draw cross section of this particular wafer, this is a cross section, this is SiO2 silicon, SiO2, I have interdigitated electrodes and I have SU8 well. This is one chip out of how many sensors are there at a time with a spacing that I have used, we can have how many sensors? We can have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right, 1, 2, 3, 4, 5, 6, 6 into 5, 30 sensors we can have, 30 sensors we have. And what we are looking here is a cross sectional or side view image of one single chip, okay. So, this is what we have seen, this is how it looks like, right, and this is what we understood a process flow. Now, once you understood this process flow, excellent, but the thing that we have discussed in the previous lecture was the mask, bright field and dark field mask, right. So, what are the bright field and dark field mask? These masks are nothing but they are made on Fe2O3 or soda lime glass. The masks are made on Fe2O3 or soda lime glass, and it is also chrome mask. The material that we use is chrome, is a chrome mask. Dimension of mask can be 4 by 4. If the wafer is, actually this is wrong, 4 by 4 is the wafer, then the dimension of the mask would be 5 inch, alright. So, if the wafer is 4 by 4 or 4 inch wafer, I can use mask which is 5 inch. Actually this is what is also correct in the way that what it is saying is I have this one is 4 by 5, this is what it is saying, 4 by 4 into 5 by 5. But in general, if what we say is just 5 inch mask, we use 5 inch mask for 4 inch wafer. So, that if you see the mask would be somewhere around, it will have somewhere around this particular area like this, right, or little bit closer. So, it will somewhere around we can have mask which is like this. For 4 inch wafer we have 5 inch mask, right, and another one is the polarity. Polarity is nothing but the positive or negative, or we can say bright field mask or dark field mask. Now, this is not always true that bright field mask is always used with negative photoresist or dark field mask is used with for positive photoresist. We have just seen an example where bright field mask can also be used with positive photoresist. Bright field mask can also be used with negative photoresist. So I believe that this sentence does not hold true in all the cases, but the mask are of two type, that is completely correct, bright field mask and dark field mask. Alright. Now, to the last point of this particular module, we have to see a very important thing, and that is the defects in the photo mask. That is, what kind of defects are there when you take a mask, right. So, there are several type of defects that you have to that you will encounter when you look at the mask. So, when you look at the mask which I have shown you in the last lecture, then what you were able to see was the pattern, but what you were not able to see was the with as close as possible or within the microscope how the mask looks like, and is there any defect in the mask or not. So, when you talk about defect in the mask, what are the defects in the mask? The first defect is a chrome spot. You will see a spot of chrome in the mask. Now, you will say, what will happen if I have a spot of chrome? This spot of chrome will destroy your whole chip, right. So, the spot of chrome is not correct. When you are going to fabricate MOSFET, this small spot will cause a big problem in your MOSFET fabrication. You cannot have this kind of defect when you are fabricating a device which are ultra small, that is in terms of microns or in terms of nanometer. You cannot make this kind of error, right. Again, when you talk about nanometers, there is another process called e-beam lithography that is used, which we are not covering in this particular course. We are covering right now photolithography, and the limitation of photolithography is that we cannot go below 2 microns, alright. But the process remains same more or less when we fabricate sensor, when we fabricate MOSFET, and we will see that a case of a MOSFET in the following lectures. What is the second defect? The second defect in the photo mask, as you can see on the screen, is the chrome extension. You see this one, this chrome is extended, right. You see this extended chrome. Then third one would be chrome bridging. There is a bridge, it is a short, right. It is a short. If I want to make interdigitated electrodes, and if I have this bridging, then there will be short circuit between two electrodes, between two digits, right. Then I cannot use this mask. So, there is defect in the mask. What is the fourth defect? Fourth defect is a pinhole. You can see this pinhole, right. What is the fifth defect? Fifth defect, clear extension. You see, is broken, clearly extension. What is the next one? Next one is clear break. You see breakage in the pattern, breakage in the pattern. So, this kind of defects in the photo mask, which are chrome spot, chrome extension, which are chrome bridging, pinhole, clear extension and clear break, this will cause a problem in the final device. That is why whenever you are given a photo mask, first you should check the photo mask in the microscope whether it is defect free or not. Then you should start experiments, alright, then you should start experiment. So, the point is, now in this particular lecture, what we have seen is how to form SU8 well, we have seen how to integrate interdigitated electrodes within the SU8 well, and then we have seen that what is the application of this particular sensor, and finally we have seen what are the defects in the photo mask, right. So, it is a combination of lot of processes that we have seen in this particular lecture, where I wanted to tell you how the process flows are used to fabricate a MOSFET. But before we go to the MOSFET, you should first look at how you can fabricate a single sensor. So, if you want to fabricate a single sensor, then you have to understand that what are the process, and whether you can fabricate single sensor on glass, or you can deposit, or you can fabricate single sensor on the oxidized silicon, or you can fabricate single sensor on the plastic. Are there any ways? So, what we have considered in this particular case is glass, which is SiO2, right. Glass is nothing but silicon dioxide, and we have taken a silicon substrate, and I have shown that if we use silicon, then we can grow an oxide. On the oxide we can deposit the metal, on the metal we can do the lithography to form interdigitated electrodes. On interdigitated electrodes we can deposit SU8, which is negative photoresist. We can again pattern the SU8 to form the well, and finally we get a sensor which can be used to measure the change in the cell properties. We can measure the change in the impedance of the tissue, and this is a biosensor. This is also called MEMS based sensor, right. So, in the next class, let us understand one by one what are the steps to from starting of the silicon wafer to growing oxide, because you have to understand when you are studying MOSFET, right, there is a field oxide and then there is a gate oxide, right. Everybody or every one of us has studied field oxide, gate oxide. There is a source, there is a drain, there is a gate, and there is a N type enhancement type MOSFET, there is a depletion type MOSFET. But how can you fabricate this MOSFET? And to understand this fabrication, the processes that we have learned today would be useful. And now I will tell you one by one, if you have a wafer, what is the technique to grow oxide on silicon wafer. Then what is the technique or what are the techniques to use to deposit the metal or deposit another material. It is metal, insulator, or it can be a semiconductor on the substrate. Then we will see what are the methods to grow a insulating layer at lower temperature, right, and we will see lithography steps little bit in detail, right. Positive photoresist, what will happen? I will take an example. Negative photoresist, what will happen? I will take an example. Today I have shown you an example, but I will show you in a different way so that you can understand further and you have more clarity on this particular process, right. Then we will take an example of the MOSFET, and in that you will understand why we are learning all these processes that I am talking today, and in another few lectures that I will be talking on why we have learned these things. When you see the process flow of MOSFET, it will be extremely clear to you what was the use of the previous lectures, alright. So, try to focus once again on this particular module. It is extremely important. There are 2 modules, my last lecture and this lecture, and combination of both will give you a sensor that can be used as a biosensor to measure the impedance, correct. Now, I hope that you understood a bit of how the sensor can be fabricated. And this process that we are using, that is also called a recipe. What is called recipe? RECEIP. Recipe is like a food recipe, right, food recipe. So, in food recipe what we do, we cook the food, right. What is the first step? Suppose we want to cook rice, what is the first step, right? You have to clean the rice, you have to put the rice in a bowl, then you put the rice in the cooker, you add the water, add your salt, right, and close the cooker, start your gas. These are the recipes, right. Same way, if you want to fabricate a sensor, you should know the process. These processes are called recipe. What is the thickness of material, what is the temperature at which we have to etch, what is the temperature at which we have to grow the silicon dioxide, right. Then what is the temperature at which the PR needs to be pre-baked, what is the temperature at which it needs to be post-baked, how much time we need to pre-bake, how much time we need to post-bake, what is the etching time. If we change the recipe, if we do not follow the recipe, what will happen? My rice will burn, right, or rice will be half cooked, right, or the water will burn. Same way, if I do not follow a proper recipe, I will not be able to get the sensor at the output. My expected output will be different, right, when I do not follow the recipe. So, recipe is very important. Process flow is also called a recipe. In the process, what is a recipe of a process? That is how we talk when we talk about microfabrication, alright. So, we will see the recipes, we will see the recipe for the positive photoresist, what is the state, we will see the negative photoresist, and we will see your MOSFET, alright. So, till then learn about this lecture, learn about this video, understand this video. If you have any doubt, you are free to ask me after you finish certain modules, then only you will be able to understand what is the role of this, right. First time when you learn something, you will have lot of questions, but maybe in following classes your answers are already there. So, first try to attend few classes, learn few classes, understand what is there, then you ask me questions. If you do not have answer, you are free to ask me questions, alright. So, you take care, and I will see you in the next class. Till then be nice, look at the videos, right, read once again, and be happy, right, that is very important. I was listening to one of the saint, I think Sadhguru, his name is Sadhguru. So, he was telling that keep laughing, right, because only dead body cannot laugh, is not it. So, if you are alive, be happy, right, keep laughing, right, live a happy life, try to live a happy life, do not take stress. Academics is one part, I am always telling you again and again, academics is a part where we can improve, right, but the reality is we are alive. So, we should live our life along with acquiring more and more knowledge, right. So, I will see you in the next class, till then you take care.